Welcome to the first of many videos covering Section 2, Linear Models. Linear models make up about 40 to 50% of the exam, so there's a lot of ground to cover. The foundation of many linear models begins with simple linear regression. This video will cover the basics of simple linear regression, including the model, assumptions, and definitions, particularly as it relates to exam SRM. Alright, let's start with the basics. Simple linear regression models the relationship between two variables, a dependent variable y and an independent variable x. We assume an additive and linear relationship between the two variables. Y is the dependent variable. It's what we're trying to predict. X is the independent variable. It's what we use to make that prediction. Beta 0 is the intercept. It represents the expected value of y when x equals 0. Beta 1 is the slope. It tells us how much y changes for a 1-unit increase in x. Together, beta 0 and beta 1 are the coefficients or parameters of the model. This model gives us the theoretical representation. But in practice, it is rare that we know the true parameters, so we need to estimate them from data. That's where regression comes in. When we have actual data, we can estimate the parameters of the model. Notice how the notation changes from the theoretical model to the observed model. Here, xi and yi represent the actual data points of observation I from our sample. The hat symbol on beta 0 and beta 1 tells us these are estimates. They're calculated from our data, not the true population parameters. More on how to calculate these parameter estimates later in the video. After we estimate the parameters, we can then use the estimated regression equation to predict the value of yi from xi, beta hat 0 and beta hat 1. The estimated regression equation replaces yi with y hat I, which is the predicted value. The approximately equal sign becomes an equal sign, since both sides of the equation are exactly equal now. A quick note on notation. In ISLR, the estimated coefficients use the beta hat notation. Freeze uses lowercase b0 and b1. Both represent the same concept of estimated coefficients. Now we get to the fun part. How do we actually find the best fitting line? Enter the method of least squares, also known as ordinary least squares, OLS, or least squares regression. Let's say we have some data points and a line that tries to fit them. The question is, how good is this line? Each data point is an observation, which we label xi, yi. These are the values we're trying to fit. The intercept, beta hat 0, is where the line crosses the y-axis, and the slope, beta hat 1, tells us how much y hat changes for a 1-unit increase in x. These vertical dashes represent residuals. Each residual measures the difference between what we observed and what the line predicted. Mathematically, the residual EI equals YI minus Y hat I. That is, the observed value minus the predicted value from our regression line. We can label each residual E1, E2, and so on. Each EI is the gap between the observed YI and the predicted Y hat I. These are exactly the quantities we want to minimize. The residual sum of squares, or RSS, is the sum of all squared residuals. We square each residual and add them up. I think I might have just said the same thing in 3 different ways. Anyways, squaring ensures that positive and negative errors don't cancel out, and it penalizes larger errors more heavily. Expanding this out, you can see that each term involves the observed yi minus the regression line evaluated at xi. To find the values of beta 0 and beta 1 that minimize the RSS, we take the partial derivatives with respect to each coefficient and set them equal to 0. As an aside, partial derivatives, maximum likelihood estimation, or any sort of calculus is very unlikely to be tested on the exam, so we won't go into the details here. However, as we delve deeper into more advanced topics, these concepts will continue to come up. And continue to be untested. Probably. Solving these equations simultaneously gives us the least squares coefficient estimates. Beta hat 1, the slope, equals the sum of cross deviations divided by the sum of squared deviations of x. It can also be expressed as the Pearson correlation coefficient R times the ratio of standard deviations. Beta hat 0, the intercept, equals the mean of y minus beta hat 1 times the mean of x. Notice that the regression line always passes through the point x bar, y bar. Here, x bar and y bar are the sample means, R is the Pearson correlation coefficient, and Sx and Sy are the sample standard deviations. The resulting equation is known as the fitted regression line. This is the line that best fits our data according to the least squares criterion. In a practical setting, there are many statistical tools that perform least squares for you, so you won't usually need to compute these by hand. But understanding what's happening under the hood is essential for the exam. So far, our linear regression model looks nice and clean, but reality is messy. Data points don't perfectly sit on a line. The approximate model does not account for random noise. Let's make it more precise. The true model includes an error term, epsilon I. This term represents all random variation and unexplained factors not captured by our linear model. Epsilon I, also called the disturbance term, represents the deviation of each observation from the true regression line. It captures everything the model doesn't. Here's a visual. The green line models the true relationship. The red dots are what we actually observe. Note that this line is different than the line from the plot we looked at earlier. The line from the previous plot was estimated from ordinary least squares. Here, we're modeling the true relationship, which, as mentioned earlier, is typically unknown. The yellow dashed lines now represent the error terms, or epsilons, instead of the residuals. It is the difference between the true relationship and the observed data, which again is largely theoretical. For our estimates to be reliable, we need some assumptions about the error terms. Let's go through them one by one. We'll also show the equivalent assumptions about the observations. Assumption 1. The expected value of yi equals the linear model. Equivalently, the true model includes the error term epsilon I. Assumption 2. The x values are non-stochastic, meaning they're fixed and known in advance, not random. This is the same on both sides. Assumption 3. The variance of each observation is constant at sigma squared. For the errors, this means each epsilon has mean 0 and variance sigma squared. This constant variance property is called homoscedasticity, which is covered in another video. Assumption 4. The observations are independent of each other. Equivalently, the error terms are independent of each other. From the central limit theorem, these assumptions imply that both the observations and the errors are approximately normally distributed. Normality is required for the t-test, but not for many other statistics of interest. Let's visualize what estimation really means and why different samples give different results. The population regression line, shown here as a dashed line, represents the true relationship between y and x. In practice, this line is unknown. We typically cannot directly observe it. Now let's randomly sample 20 data points from this population and fit a least squares line. The blue line is our estimate, the best we can do with this particular sample. But what if we had sampled different data points? Let's see what happens. We observe that a different sample gives a different least squares line. The slope and intercept change each time. Each sample produces a slightly different estimate. This variability is called sampling variation. In practice, the population regression line remains unknown. If we had the entire population, there would be no need for estimation, since we could use the true population parameters. Let's work through an example, step by step. A researcher is studying the relationship between hours of study per week and test scores. Here's our data. 5 students with their hours of study and corresponding test scores. Our goal is to use OLS to fit a regression line and use it to predict the test score for a student who studies 6 hours per week. So here's the game plan. To fit a regression line, we need 2 coefficients, beta hat 1, the slope, and beta hat 0, the intercept. But to compute those, we'll first need the means, x bar and y bar. Once we have our regression equation, we simply plug in x equals 6 to get our prediction. Let's start by calculating the means. The mean of x is 2 plus 3 plus 5 plus 7 plus 8 divided by 5, which gives us 5. The mean of y is 70 plus 75 plus 80 plus 85 plus 90 divided by 5, which gives us 80. Next, we'll compute the slope. We use the beta hat 1 formula. We need to calculate the numerator and denominator separately. For the numerator, we multiply each x deviation by the corresponding y deviation. That's negative 3 times negative 10 plus negative 2 times negative 5, and so on. Adding those up gives us 80. For the denominator, we square each x deviation and sum them up. 9 plus 4 plus 0 plus 4 plus 9 equals 26. So beta hat 1 equals 80 over 26, which is approximately 3.08. This means for each additional hour of study, the test score increases by about 3.08 points. Step 3, the intercept. Beta hat 0 equals y bar minus beta hat 1 times x bar. That's 80 minus 3.08 times 5, which equals 64.6. The estimated regression line is y hat equals 64.6 plus 3.08x. This is the best fitting line through our 5 data points. Now let's use our equation to make a prediction. If a student studies 6 hours per week, the predicted test score is 64.6 plus 3.08 times 6, which equals approximately 83.08. Let's see this visually. Here are our 5 data points plotted and the regression line running through them. And here's our prediction. At x equals 6, the model predicts a test score of about 83.08. The dashed lines show exactly where this point falls on both axes. Of course, this is a simple example. In practice, it may not be possible to score greater than 100, and at some point, each additional study hour may not contribute as much to the score as the previous one, so a simple linear model may not be the best fit. There are many other models and fits that can be used, which we'll cover in other videos. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.